Hi students, good morning to all of you. Hope you are all doing good. Welcome to Lecture 5 in Theory of Equations. Hope you have reviewed the first 4 lectures. In this lecture, I will be discussing the trial and error method of solving a polynomial equations, and I will solve some cubic and biquadratic polynomial equations with the given information on the roots actually. Okay? Okay, let us consider an nth degree polynomial f of x as shown here. Now we will discuss the trial and error method. Okay, so basically this trial and error method is a method to find out root of a polynomial equation f of x is equal to 0. So what actually we need to do? We need to find out a value of f of x for which f of x is equal to 0. So in this trial and error method, what we will do is first you come up with some number alpha, whether it is be it be real or a complex number, and you claim that that is a root. Okay. Now you check whether it is a root of the polynomial equation f of x is equal to 0 or not. Okay. Now, what you will do, you just check whether it is a 0 or not. How to check whether alpha is a 0 of f of x is equal to 0? You just substitute that alpha in that equation. You will get f of alpha. If f of alpha is equal to 0, then you can claim that alpha is a 0 of that polynomial equation. If it all f of alpha not equal to 0, then you can say alpha is not a root. Okay, if f of alpha is equal to 0, it is well and good. You found out one root of a polynomial equation. If at all f of alpha not equal to 0, then you come up with some other real or a complex number and you repeat this method till you get a 0 of a polynomial equation. Okay, but the problem with this method is the set on which you are searching for a 0 is very big. Basically, you are getting all these alphas, okay, from the set of real or a complex number, and you know the size of reals or complex numbers is really massive. Okay, this method will not work on this kind of sets. That means on the infinite sets actually. Okay, if the size of the set is small, at least this method will work. That means we try to get a solution from that finite set. Okay, so here we are going to discuss some special types of polynomials for which you can find out some special types of zeros. So those special types of polynomials, which I am talking about is the polynomials with integer coefficients. And those special types of zero which I am referring to is the rational zeros of the polynomial with integer coefficients. Let us see a method to find out the rational zeros of it. Okay, so here the criteria is to find out the rational zeros. So if the polynomial has integer coefficients, then every rational zero of f of x is equal to 0 will be of the form p by q, where p and q has no common factor other than 1. That means the GCD of p and q, okay, or HCF, highest common factor is 1. Highest common factor of p and q is 1, or the greatest common divisor of p and q is 1. Okay, then see, where p is a factor of a constant term an and q is a factor of a leading coefficient a naught, then the possible rational zeros are factors of the constant term an divided by factors of the leading coefficient term a naught actually. Okay, let us discuss some examples. Here is the question: find all the possible rational zeros of the given cubic equation. Okay, we have to find out all the possible rational zeros. So here is the answer. The possible rational zeros are plus or minus this one, as we discussed in the last slide, what we need to do is the the constant term an is equal to 3 and a naught is equal to 2. Okay, the factors of the factors of an the factors of an is equal to plus or minus 1 comma plus or minus 3, and the factors of a naught, that is equal to, that is a naught is equal to 2. So here also we'll be getting plus or minus 1 comma plus or minus 2. Now we have to find out the rational zeros. What are the possible rational zeros? Possible rational zeros are plus or minus 1 divided by plus or minus 1, plus or minus 1 divided by plus or minus 2, comma plus or minus 3 divided by plus or minus 1, comma plus or minus 3 divided by plus or minus 2. So all these put together we get this one, plus or minus 1, plus or minus 3, and plus or minus 1 by 2, and plus or minus 3 by 2 actually. Okay. Now let us find out whether these numbers are zeros or not. Okay. Let me consider my f of x is equal to the given polynomial. Now we are finding out f of one value. So let me erase this part, and you can see that this is going to be f of 1. F of 1 is equal to 0. That means what? 1 is a root of the equation. Now let me find out f of minus 1. So minus 1, if you find out, you get 12, which is not equal to 0. So this is a rejected rational root. Now let me test the next root, that is 3. You just substitute 3 in the given equation and you can see this is not equal to 0. So alpha is equal to 3 is not a 0. Next, f of minus 3. F of minus 3 is what? 2 into minus 3 whole cube, that is minus 54 plus 27 plus 24 plus 3. So this is equal to 0. So we can say this is actually the zero of rational zero of the given polynomial equation. Next one, f of half. Okay, you try with half, then you can see that this is also becoming 0. This is also becoming 0. Okay, now anyway we have got the 3 zeros. This is one more thing. So this is one more thing. So we have got 3 roots. Even if you test the other numbers also, anyway you will not get, because a cubic equation has at most 3 particular roots. Okay. Now let me find out the other values of f at the other roots. So f of minus 1 we have missed, and if you find out those values, that you get it as 15 by 2, which is not equal to 0. And similarly you just substitute 3 by 2, okay, in the above equation, and we can see that this value is not equal to 0. Now f of minus 3 by 2 is just try. So this particular thing, if you solve, you'll be getting 15, which is not equal to 0. So these are all not the roots. These are not the roots, rational zeros of a given polynomial equation. So we have got all the 3 rational zeros of the given polynomial equation. Okay, let me discuss the rational zeros of the equations are 1 comma minus 3 comma 3 by 2 actually. Okay, now let me consider one more example on this. Find the possible rational zeros of x power 4 minus x cube plus x square minus 3x minus 6 is equal to 0 actually. Okay, so here what is the leading coefficient? Leading coefficient is an is equal to, sorry, leading coefficient is a naught is equal to 1, an is equal to minus 6. Okay, so what are all the factors of minus 6? This is plus or minus 6, comma, plus or minus 2, comma, plus or minus 3. And this a naught is equal to 1. A naught is equal to 1. So what is that you have to do now? So possible rational zeros are possible rational zeros are plus or minus 1, plus or minus 3, plus or minus 2, comma, plus or minus 6. Okay. Now f of x is equal to x to the power 4 minus x cube plus x square minus 3x minus 6 is equal to 0. Then you find actually we are trying whether one is a root of the equation or not. So 1 power 4, if I substitute it, then it is not getting 0. So this is not equal to 0. Then f of minus 1. So upon substituting x is equal to minus 1 in the above equation, we get this as 0. So this is one more challenge. F of minus 1 is equal to 0. Let me discuss one more example. Here is the example. Find the possible rational zeros of the equation x power 4 minus x cube plus x square minus 3x minus 6 is equal to 0. So as discussed in the beginning, okay, let me find out what is an here. An is equal to minus 6 and a naught is equal to 1. Okay, so the possible factors are possible factors. So possible factors are plus or minus 1, plus or minus 2, plus or minus 3, comma, plus or minus 6. So possible factors of an are this one. And possible factors of a naught is equal to 1. A naught is equal to 1 or plus or minus 1. Therefore, according to that rule, the possible rational zeros are plus or minus 1, comma, plus or minus 3, comma, plus or minus 2, comma, plus or minus 6 divided by plus or minus 1. So the possible rational zeros are plus or minus 1, comma, plus or minus 3, comma, plus or minus 2, comma, plus or minus 6. Let us find the values of f at these values. Okay, f of 1. Let us find out f of 1. F of 1, if you find out this value, this is equal to minus 8, which is not equal to 0. So this is not a rational 0. Now let me find out f value at minus 1. So you can see that minus 1 whole to the power 4 minus of minus 1 whole cube minus 1 whole square. This is becomes 0. So then this is also a root. Now we find out f3, and this is not equal to 0, so this is not a root. And substituting minus 3 in the above equation, then you get 120. 120 is not equal to 0, so minus 3 is not a 0. Now f of 2. F of 2 is equal to 0, you can say. So 2 is a root in this particular case. Next, f of minus 2. F of minus 2 is minus 2 whole power 4 and so on, and this value is equal to my 28. This 28 is not equal to 0, so 2 minus 2 is not a root. Okay, and f of 6 is not equal to 0 anyway. F of minus 6, if you compute, then also you can see this is not equal to 0. So here 6 comma minus 6 are also not the roots. Okay, so the possible rational roots are the rational zeros of the equation are minus 1 comma 2 actually. Okay, so these are the minus 1 comma 2, minus 1 comma 2. Minus 1 comma 2 are the zeros of the given polynomial equation. But one thing I am going to tell you is this method only gives us a way to find rational zeros if at all they exist. I am not telling that if at all if you apply this method you'll get a zero. No. If at all a polynomial equation has a rational zero, then finding rational zeros will be easy if you follow this method. Okay. In the next slide, we are going to discuss some points here. So when a root a of the equation f of x is equal to 0 is known or obtained by the trial and error method, then x minus a is a factor of the polynomial f of x, and by dividing the equation by this factor, we can reduce the degree of the equation by 1 and solve the resulting equation. That means what? If you find by some method or by some information a is a root, then you divide the given polynomial by the linear factor x minus a. You can use Horner synthetic division method to find out the quotient actually. We can reduce the degree of the equation by 1 and we can solve the resultant equation. Okay. And when a relation between the roots of the equation f of x is equal to 0 is given, using this information, you can factorize the equation and therefore solving the equations easily. You know the relations between the roots and the coefficients, namely s1 is equal to alpha plus beta plus gamma, s2 is equal to alpha beta beta gamma plus gamma alpha, s3 is equal to alpha beta gamma. Now you will be given some relation between roots and the coefficients. Okay. Now depending on that information, okay, you can solve the polynomial equation. Okay. Now some information will be given on the roots. If some information on will is given on the roots, then how to consider the roots? In case of a cubic equation, we are discussing it. The three roots of a cubic equation are in arithmetic progression. Then how do we consider the three terms, the three roots as? The three roots we consider as a minus d, a comma a plus d. The advantage with this three roots is if I take the sum, then this minus d and plus d gets cancelled, then you will be getting 3a. So finding 3a becomes easy. Okay. And s1, sum of the roots is equal to what? S1. S1 is equal to 3a. So from a is equal to what? S1 by 3. So you'll get the root directly. After getting the root, you can divide the polynomial, given polynomial by x minus a. Then you get the quotient polynomial. You try to solve the quotient polynomial. Okay. Now the next one is three roots of the cubic equation are in geometric progression. Then consider the roots as a by r comma a comma ar, where r is a common ratio of the geometric progression. Okay, now here in this case, what you need to do is you have to consider the product. If I consider the product, then I'll be getting what? A by r into ar, that is equal to a cube. So product of the roots is equal to S3. So S3 is equal to my product of the roots. So the product of the roots is A cube. A cube is equal to S3. A is equal to what? S3 whole to the power 1 by 3. Thereby you'll get one root. Once you get one root, you can divide it by a linear polynomial x minus a, and you'll be end up with a quotient polynomial, and you solve a quotient polynomial because it's in anyway quadratic equation. Next one, the three roots of the cubic equation are in harmonic progression. Then you consider the roots as 1 by a minus d, comma 1 by a, comma 1 by a plus d, where d is a common difference. And you know very well, when do we say that three terms are in harmonic progression? If their reciprocals are in arithmetic progression. What is the reciprocal of 1 by a minus d? It is a minus d. Okay, so if I assume this, if you assume these as my roots, then solving becomes easy because you have only two unknowns here. Next one is two of the three roots are equal. Two of the three roots are equal means alpha comma beta are the roots. We consider alpha comma beta as the roots of the equation, and then plug in in the relation between the roots and the coefficients, and you will try to get the solution for it. Sum of the two of the three roots is 0, then we consider the roots as alpha comma minus alpha comma beta are the roots. And two of the three roots are in the ratio m is to n, then it becomes m alpha comma n alpha comma beta. These are the roots in this particular case. Now let me get into the next slide, which shares some information on a biquadratic equation. So this is the information given on the roots of a biquadratic equation. Four roots of a biquadratic equation are in arithmetic progression. And then how do we take the roots? A minus 3d, a minus d, a plus d, a plus 3d, where 2d is the common difference. Why did we take like this? If I take up the sum, a minus 3d plus a plus 3d, that is 2a, a minus d plus a plus d, if I compute that, then it becomes 4a. 4a is equal to what? The summation. So 4a is equal to s1, a is equal to what? S1 by 4. So you'll get a value. Okay, once you get the a value, you can find out the d value by looking into those relations between roots and the coefficients. Next one, four roots of a biquadratic equation are in geometric progression. Then you consider the roots as a by r cube comma a by r, ar and ar cube, where r square is a common ratio. And the next one, four roots of a biquadratic equation are in harmonic progression. Then you take the reciprocal of whatever the case we have discussed in the first. And pair of equal roots for a biquadratic equation, then you have to assume the roots as alpha, alpha, comma alpha, comma beta. Sum of the two of the four roots is 0, then alpha minus alpha comma beta and gamma are the roots of the equation. Okay, next one, two of the four roots are in the ratio m is to n, then we consider the roots as m alpha comma n alpha comma beta comma gamma. These are the roots. Okay, if this information is being given on a cubic or biquadratic equation, we have to, if we follow this, then our job becomes easy to solve, find out the roots actually. Okay, let us solve some problems in exercise 4a. Here is our first problem in this. Solve x cube minus 3x square minus 16x plus 48 is equal to 0, given that sum of two roots is 0. Let us write down the solution for this. So here is the solution. It is given that sum of two roots of the given equation x cube minus 3x square minus 16x plus 48 is equal to 0 is 0. So in this case, let alpha comma minus alpha comma beta be the three roots of the equation. We have seen why we have to take alpha comma minus alpha as two roots. Okay, now consider S1. S1 is equal to what? Sum of the three roots. Sum of the three roots is equal to what? Alpha minus alpha plus beta. That is equal to what? Minus of minus 3. So that is equal to 3. Implies beta is equal to 3. Okay. This means one root of the equation we have got it. One root of the equation is beta is equal to 3. Now we have to find out the remaining two roots. So how to find out the remaining two roots? Let us take S2. S2 is equal to what? Alpha into minus alpha plus minus alpha into beta plus beta into alpha. That is equal to what? this is minus 16. So this implies this is minus alpha square, this is alpha beta plus alpha beta is equal to minus 16, implies minus alpha square is equal to minus 16, implies alpha square is equal to 16, implies alpha is equal to plus or minus 4. Okay, so the roots are, so the values of alpha are plus or minus 4. Therefore, the roots of the equation are alpha minus alpha beta, that is equal to 4 minus 4 comma 3 if your alpha is equal to 4. Now again, if I take my alpha is equal to minus 4, if alpha is equal to minus 4, then this becomes minus 4 comma 4 comma 3. So this implies the roots of the equation are 4, 4, 3. Let us solve one more problem. Here is our next problem. Find the condition that x cube minus px square plus qx minus r is equal to 0 may have sum of two of its roots as 0. Now we have to find out the condition if sum of two roots of a cubic equation is 0. Okay, let us solve this question. Here is the solution. Given that sum of two roots of the equation x cube minus px square plus qx minus r is equal to 0 is 0. So in this case, let alpha comma minus alpha comma beta be the roots of the given equation. Okay. Now let us consider S1. S1 is what? Alpha minus alpha plus beta. That is equal to what? Minus of minus p. That is equal to p. So this implies beta is equal to p. So one root of the equation is beta is equal to p. Okay, to get the condition, since beta is equal to p is a root, it must satisfy the given equation. So p cube, let me substitute that p in the given equation, p into this is p square plus qp minus r must be equal to 0. So this implies p cube minus p cube plus p cube minus r is equal to 0 implies p cube minus r is equal to 0. So this is our required condition. Okay. Let us solve the next question. Here is our next question. Given that roots of the cubic equation x cube plus p 3p x square plus 3qx plus r is equal to 0 are in arithmetic progression, then show that 2p cube minus 3p cube plus r is equal to 0. Okay, so what we have to do is, given that the roots of the roots of the equation are in arithmetic progression, then we have to show that this PQR satisfies this relation. Okay, let us solve this particular problem. solution. We have seen previously, if the roots of the cubic equation are in arithmetic progression, how to take the roots. Given that roots of the equation x cube plus 3p into x square plus 3q into x plus r is equal to 0 are in arithmetic progression. Okay. Now let me take my roots as, let a minus d comma a plus d be the roots of the given cubic equation of the equation. Okay. Now let me consider my S1. What is S1? S1 is a minus d plus a plus a plus d. So this is equal to what? Minus 3p. So implies 3a is equal to minus 3p. Implies a is equal to minus p. Observe that a is one of the roots. Okay. So this implies one root of the equation given equation is minus p. This implies minus p satisfies the given equation. Minus p satisfies the given equation. That means we have to substitute here. This implies minus p whole cube plus 3p into minus p whole square plus 3q into minus p plus r is equal to 0. So this implies minus p cube is minus p whole cube is minus p cube plus 3p cube minus 3 into p cube plus r is equal to 0. So this is minus p cube, this is 3p cube, this becomes 2 into p cube minus 3p cube plus r is equal to 0. So this is what we are supposed to prove actually. Hope you have understood the solution. Let us solve one more problem. Here is our next problem. Given that the roots are in roots of x cube plus 3p x square plus 3qx plus r is equal to 0 are in geometric progression, then show that p cube into r is equal to q cube. Okay. Now let me solve this equation. Let me try to find out the solution for this. It is given that roots of the equation x cube plus 3p x square plus 3qx plus r is equal to 0 are in geometric progression. We know how to take the roots. Let the roots are, let a by r comma a comma ar be the roots of the equation. Okay, with the common ratio r. You can see if I multiply the first term, I'll get the term a. If I multiply r with r to a, then I'll be getting ar. Okay. Now consider S3 is equal to a by r into ar, that is equal to a cube. So S3 is equal to what? Minus r. So implies a is equal to minus r whole to the power 1 by 3, which is a root of a given equation, which is a root of the given equation. Okay, so this implies a is equal to minus r whole to the power 1 by 3 will satisfy the given equation. Will satisfy the given equation. Okay, so let me substitute in this equation, then I get, so minus r whole to the power 1 by 3 whole to the power 3 plus 3p into minus r whole to the power 1 by 3 whole square plus 3q into minus r whole to the power 1 by 3 plus r is equal to 0. So minus r whole to the power 1 by 3 whole cube is equal to what? Minus r plus 3p into minus r whole to the power 1 by 3 whole square. This is 2 by 3. Okay, plus 3q into minus r whole to the power 1 by 3 plus r is equal to 0. Now this minus r and r gets cancelled here. Okay, this implies 3p minus r whole to the power 2 by 3 plus 3q minus r whole to the power 1 by 3 is equal to 0, implies p into minus r whole to the power 2 by 3 is equal to minus q into minus r whole to the power 1 by 3. So upon cubing we get, so p cube into minus r whole square is equal to minus q cube into minus r. So this implies p cube into r square is equal to q cube into r. So this implies r into p cube into r minus q cube is equal to 0. As r is not equal to 0, implies p cube into r minus q cube is equal to 0, that is p cube r is equal to q cube. So this is what we are supposed to show. Hope you have understood that. See, whenever you are taking the roots, whenever the roots are in geometric progression, you consider the roots as a by r, ar, and consider the product, then immediately you will get one of the roots actually. So if you get one of the three given roots, you can find out the other two roots very easily. In the case of in the case when roots are in arithmetic progression, you have to consider the roots as a minus d, comma a plus d, and there we took the summation, actually the sum of the roots, s1, a minus d, a, and a plus d. If I take the sum, then it becomes 3a. You'll be getting one root directly there. So this is how we have to proceed when the roots are in geometric progression or in arithmetic progression. Okay. Here is our next problem. Given that the roots of the equation x cube plus 3px square plus 3qx plus r is equal to 0 are in harmonic progression, then we have to show that 2q cube is equal to r into 3p cube minus r. Okay. Let us try to find out the solution for this. Solution: given that roots of the equation x cube plus 3px square plus 3qx plus r is equal to 0 are in harmonic progression. So this is harmonic progression. Okay, so let me take my roots as 1 by a minus d, 1 by a comma 1 by a plus d be the roots of the given equation. Okay, now let me take this as my alpha, my beta and my gamma. Okay, now let me write what are s1 here. S1 is equal to alpha plus beta plus gamma, that is equal to minus 3p, and s2 is equal to alpha beta plus beta gamma plus gamma alpha is equal to 3q, and my s3 is equal to alpha beta gamma, that is equal to minus r. Okay, now consider 1 by alpha plus 1 by beta plus 1 by gamma, that is equal to, this is alpha beta gamma, so this becomes beta gamma plus alpha into gamma, and this is alpha beta. If you look at this quantity, this is equal to s2 and this is equal to s3. So let me substitute what is 1 by alpha here. 1 by alpha is a minus d plus a plus a plus d, that is equal to s2. S2 is 3q divided by minus r, that is equal to minus 3q divided by r, implies 3a is equal to minus 3q divided by r, implies a is equal to minus q divided by r. So this implies 1 by a is equal to minus r by q is one root of the equation. One root of the equation. Okay, and let me continue in the next page. Here is the continuation. So we have got one root, that is 1 by a is equal to minus r by p of the equation. So this implies it satisfies the given equation. So I think this is q. Okay, so after substituting the given equation, this is minus r by q whole cube plus 3p into minus r by q square plus 3q into minus r by q plus r is equal to 0. So this implies minus r cube divided by q cube plus 3p into r square divided by q square minus 3r plus r is equal to 0. So this implies, so if I consider the first two terms, then the LCM is q cube, this is minus r cube plus this is 3p cube into r square, this is minus 2r is equal to 0, implies 2r into q cube is equal to minus r cube plus 3pq into r square. Now take r common, then I get 2q cube plus r square minus 3pq into r is equal to 0. This implies as r not equal to 0, we get 2 into q cube plus r square minus 3pqr is equal to 0. So this implies 2q cube is equal to 3pqr minus r square. So that is equal to r, if I take common, it is 3pq minus r. So what do we get? So 2q cube is equal to r into 3pq minus r, which is the required condition that we have to prove. Okay, let us continue the problem in the next page. So I'm continuing the problem here. So we get alpha square plus 10 alpha by 3 minus 4 alpha square is equal to 7 by 9. So alpha square minus 4 alpha square is minus 3 alpha square plus 10 alpha by 3 minus 7 by 9 is equal to 0. Implies. So the LCM is 9 here. So it is minus 27 alpha square plus this is 30 alpha minus 7 is equal to 0. So we get minus 27 alpha square plus 30 alpha minus 7 is equal to 0. We get 27 alpha square minus 30 alpha plus 7 is equal to 0. So upon multiplying, we will be getting this equation. So we have to solve this equation in order to get the values of alpha. Okay. Now this 27 alpha square minus 30 alpha plus 7 is equal to 0. So 27 into 7, this can be written as 9 into 3 into 7. So this is my 21. 21 plus 9 is 30. So this can be written as 27 alpha square minus 9 alpha minus 21 alpha plus 7 is equal to 0. So this implies if I take 9 alpha common, this becomes 3 alpha minus 1 minus 7 if I take common. So 3 alpha minus 1 is equal to 0. So this is 3 alpha minus 1 into 9 alpha minus 7 is equal to 0, implies alpha is equal to 1 by 3 or alpha is equal to 7 by 9. So here there are two possible values for alpha. Now there is only one particular choice possible because both of them cannot be the roots actually. Okay, so let me check. Let us check for let us check let us check for the root. So to check whether it is a root or not, I have to substitute alpha is equal to 1 by 3 in the equation. Put alpha is equal to 1 by 3 in the equation, in the given equation. What do we get here? So it is 9 into 1 by 3 whole cube minus 15 into 1 by 3 whole square plus 7 into 1 by 3 minus 1 is equal to, so this is 27, this is 9 minus, this is 9, so LCM is 27, so it is 3 into 15, that is 45, plus 9 into 7, that is 63, minus 27. So 63 plus 9 is 72, minus 72 divided by 27, that is equal to 0. So this implies alpha is equal to 1 by 3. Alpha must not be equal to 7 by 9. Okay. So this implies beta is equal to 5 by 3 minus 2 alpha, that is 5 by 3 minus 2 into 1 by 3. So that is 5 minus 2, that is 3 by 3, that is 1. So beta value is equal to 1. Therefore, the roots of the equation are 1 by 3, comma 1 by 3, comma 1. Okay. So this is how one can find out the roots. Okay.